Hi there, welcome to week 2 of HackadayU serial buses with me, Alexander Rowsell. My email is there on screen again. Congratulations to David Choi, who won the $10 Tindy gift certificate by finding last week's Easter egg. He found it very quickly after the video went up, so good on him. The Easter egg was the EEPROM data that I was reading from that EEPROM actually spelled out HackadayU, exclamation mark. So congratulations to him. And enjoy your $10 Tindy gift certificate. Hopefully you can find something really cool to buy. So now we're going to be diving into the MSP 430F5529, I2C implementation. The steps are going to be specific to this chip, but I'm going to generalize it as much as possible for all chips. So a quick recap of last week. We looked at I2C from the hardware and protocol level. This week we're going to be looking at I2C implementation in software and how that works with hardware and protocol. Last week's lesson is fairly vital to understanding the content in this week's lesson, so if you haven't seen last week's, you might want to go watch that first. If you already know how I2C works and you just want to see some hardware examples, software examples of hardware implementation, you could just watch this lesson on its own. If you haven't watched week 1, good idea to watch that one first. So most data sheets still use problematic language. We talked about this last week. We're going to be avoiding those usages wherever possible, and we're going to be continuing to use controller and peripheral as we have done so far in this course. So, software level. There are two main approaches to implementing an I2C controller. Using a hardware peripheral if available. Most modern microcontrollers have these, or you can implement it using GPIO commands, which is also known as bit banging. There's advantages and disadvantages to either approach. Hardware peripherals take care of all the bus timing, clock generation, acknowledge, not acknowledge, start and stop. We can focus for the most part on just sending and receiving data. We have to monitor interrupt flags and monitor status registers and set things up, but for the most part it takes care of the nitty-gritty for us. Software implementations, where bit banging, for example, they allow us total control, but at the cost of processor usage. Often you're going to be implementing delays between each successive bit or byte, using literal just loops in assembly code, so NOPs looped over and over. So your processor usage is going to be very high, which means it's going to limit you to just doing one thing at a time. This can sometimes be necessary to circumvent bugs in the hardware controller, or if we don't even have a hardware controller on the microcontroller we're using. Older microcontrollers often didn't have I2C peripherals built in, so you would have to write it in software, doing bit banging with the GPIO. Or there may not be enough I2C buses on the microcontroller. We can add additional I2C buses in software. So all the examples are going to be written in C++, but my C++ looks a lot like C because I learned C and used C for a long time and have been recently migrating to using C++ in embedded. If you've worked with Arduino, it'll look very familiar. So a list of microcontrollers that have I2C hardware. Most microcontroller families do have it. MSP 430 and 432, almost all of them do. Most PICs do, except for the smallest PICs like the PIC-10. The STM8 and 32, almost all of them do. Almost all the Atmega and AT-Tinys do, except for the very smallest ones. And any microcontroller that's based on an ARM Cortex-M, no matter what size it is, 00, 347, it's going to almost certainly have an I2C bus, at least one. 8051 based microcontrollers usually don't have I2C peripherals. They usually have just very basic peripherals. Some microcontrollers, like the I2C series from Texas Instruments, can have like 11, 12 hardware I2C buses on the chip, which is just insane. It's very important to check the data sheet for the microcontroller you want to use. Yeah, the I2C series can have many buses per chip. So the most important thing to do when you're implementing anything, but especially I2C or any serial bus, is to gather information. You need to be able to quickly find data that is relevant to your application. Many microcontroller data sheets and family reference guides are hundreds, sometimes thousands of pages long. We're going to be going over examples with the 5529, but the same techniques apply to any microcontroller. You need to find the section of the datasheet or the family reference manual pertaining to I2C, and you might also need to refer to the section on GPIO, remapping peripherals, or clock structures. In the case of the MSP430, we actually do need to refer to both GPIO and the clock structure. Well-written datasheets will include references to the parts of the datasheet that are relevant to using that peripheral. Make use of all available resources. Look at example libraries or example usage code. Look for open source projects that use the same chip and peripheral. If you're running into confusing errors, this is something that bit me recently, check the errata page for the chip you are using. Sometimes hardware bugs are the issue, and there will be workarounds in the errata on how to fix those. So your terminology is going to vary from microcontroller family to family. Atmel calls I2C TWI, for example. Other terms will vary from chip to chip. Some manufacturers combine all their serial buses into a single block. This is how the MSP430 does it. It calls it the Universal Serial Communication Interface. You get a couple of these blocks, and each one can be configured as UART, SPI, or I2C. Other microcontrollers will have each serial bus in their own block. This is how many other manufacturers do it. Either way, the setup process is broadly similar. There's only one difference, essentially. And the process we cover here can easily be adapted to other chips. When you're in doubt, read the datasheet carefully, utilize all the resources you have at hand. Register names and layouts are going to differ greatly, but the options and configuration bits that you are able to choose from will be similarly grouped in most cases because, of course, things go together logically. For example, most microcontrollers have baud rate as a separate register. They'll have the peripheral address as a separate register. They'll often have both transmit and receive buffers for incoming and outgoing data, that sort of thing. So let's take a look at the general setup process. So generally, the following steps are taken. You make sure the I2C peripheral is disabled. You put it into reset if applicable. Some require you to enable a reset bit. It's a bit often called on or reset or something similar to that. Select the pins you want to connect to. Sometimes you are restricted to a certain subset of pins. Others can be connected to a range of different pins using an interconnect matrix. This is how the PICs do it. You can select from a subset of pins to put your I2C bus on. On the MSP430, you're hardwired to particular pins. Configure the speed of the bus, so decide whether you're going to be running at 100 kilohertz, 400 kilohertz. Usually this is going to be, you have to calculate a divisor based on the clock speed of the chip. Some chips have separate clock systems just for the peripherals, so make sure that you have the clock system set up correctly, or just look up what the defaults are for the chip you're using and then make sure you base it on that. The datasheet should tell you which clock it's based on, or it'll let you pick which clock you want to derive your baud rate from. Sometimes there's a formula that goes along with it. Sometimes it's as simple as dividing. Say you're running at 6 megahertz and you want to run at 100 kilohertz, well, your divisor is going to be 60. Sometimes you have to divide by 32 or multiply by 8. Sometimes there's a prescaler value you can add, which can be useful if you're running at a very high clock rate. Say you're running at 100 megahertz, but you want to run at 100 kilohertz. Normally that would be quite a big divisor, but if you add a prescaler to the clock of 2 or 4, that divides it down first, and then you can divide it down more using the actual baud rate divisor. Set the peripheral into I2C mode if applicable. As I said, this is how it works on the MSP430. You have to tell it, I want this block to operate as I2C. Sometimes you need to do this immediately after putting the block into reset. If you need to, the datasheet will tell you. Then enable the peripheral and communication can commence. So it's just a few simple steps. This will apply to pretty much all I2C hardware peripherals across all microcontrollers. These steps might be in a different order. There might be other little caveats depending on the chip, but these are the goals that you need to get done. So specifically on the F5529, let's go take a look at the Family User's Guide, and we're going to take a brief look through it at how initialization and reset works. And in a minute, we're actually going to be going and looking at the PDF. But for initialization and reset, this is the very first step. So in the F5529, the reset bit is called UCSWRRST, SWRST, which stands for software reset. So you only configure or reconfigure the module when that software bit is set. So that's the very first thing we need to do. If you look down below, initializing or reconfiguring the USCI module, the recommended process is to set that reset bit, initialize all the USCI registers with whatever you need to set them to, configure the I/O ports, then clear the software reset bit, and you can then enable interrupts if you want to. So data sheets will usually have a step-by-step list because there may be reasons why things need to be done in a certain order. So configuring speed, which is the next step, after the module is put in reset for the MSP, we then have to set the speed of the bus by calculating the values for the baud rate registers. So all the registers on the MSP 430, because the block is called the Universal Serial Communication Interface, all of the blocks start with UCB and then a number. We're using block number 1, so they're all going to start with UCB1. So all we really need to look at is those last letters, BR0 and BR1. This is a 16-bit value, so we can divide the clock by up to 1024. So we need to very carefully calculate what that baud rate divisor is going to be, see if it fits in 16 bits or just 8 bits. Here's the actual description of those registers from the data sheet. You can see we can only modify these when that reset bit is set. So that's really important to set the reset bit and then do all your configuration. As you can see, the prescaler is a 16-bit value. It's BR0 plus BR1 times 256, so it's just concatenating these two bytes together to make a 16-bit value. Simply treat them as a 16-bit value. For a 6 megahertz peripheral clock, to get 100 kilohertz, our divisor would be 60. It's a 16-bit value, partially because the MSP 430 is a 16-bit processor, but also because we might need to divide by more than 255, especially if you're running at a higher clock speed. After that, we need to set up the control registers. On the MSP 430, there's 2 control registers that configure how the I2C module is set up. Control 0 and control run. Remember, we can ignore UCB1. That's going to be present in front of all of these register names. These set things like the peripheral address length, whether it's going to be 7-bit or 10-bit. Almost all the time we'll be using 7-bit. Whether we are currently acting as the controller or the peripheral, because of course the MSP 430 can act as a peripheral and let another chip control the bus and act as if we're a sensor or something. This will also set whether we're currently transmitting or receiving, as well as there's bits to generate start conditions, stop conditions, acknowledge, not acknowledge, all the hardware bits that we looked at last week. For initialization, we just need to make sure that we have them set up for I2C mode, acting as the controller. And this process is generally similar on all microcontrollers. You're going to be setting whether you want 7 or 10-bit peripheral addresses, whether we are acting as the controller or the peripheral, and then there's going to be bits to generate start conditions, stop conditions. Let's take a closer look at this part of the datasheet just to show you exactly how it's done on the MSP 430. Alright, so here is the family user's guide for the 5 and 6 series MSP 430s. These are the higher end, more powerful chips. These are all the different peripherals on the side, but of course we're interested in the Universal Serial Communication Interface running in I2C mode, so section 38. And we're going to take a look specifically at the registers. I just want to show you what things you'll typically find in configuration registers. So here's control 0. So there's each of these is a single bit that you set in these registers, and they configure different things. If we're acting as a peripheral, do we want to use a 7-bit or a 10-bit address? If we're acting as the controller, does the peripheral have a 7-bit or a 10-bit address? Are there more than one controller on this bus? If it's a single controller environment, then we don't need to worry about stuff like bus arbitration or address comparison, that sort of thing. Whether we are currently a controller or a peripheral. And then this is the bit, this UC mode X bit. This is what actually changes the type of universal serial communication interface. We have 3-pin SPI, 4-pin SPI, I2C mode, and then below that we have both asynchronous and synchronous mode. I2C is always synchronous, and this is actually set to a 1 by default for us, which is kind of nice. Actually, that's a read-only, so that's just telling us what it's set to. And then here's the control 1 register. Again, we can choose what clock source we want to clock the I2C peripheral from. These terms, A clock, SM clock, these are unique to the MSP430. They'll be called different things on different chips. SM clock on the MSP430 is the peripheral clock. So there's M clock, which is the clock that goes directly to the CPU. Then there's SM clock, which goes to all the peripherals. The reason that chips do this is because it gives you more control over power consumption. If you want to just turn off the peripherals, you can, or even just reduce power usage, you can slow down the clock on the peripherals or on the CPU while leaving the peripherals running at full speed. That's why they're split up. On simpler chips, it'll just be all one clock and you won't need to worry about the clock source selection. Whether we're currently acting as the transmitter or receiver, this bit will essentially change that read-write bit. Remember, at the end of the I2C peripheral address, we have that read-write bit to tell the chip whether we want to write to it or read from it. That's what this bit is going to set for us. There's a bit here to transmit a NAC. This is obviously if we're reading data, like we saw last week in that example. I read 10 bits from that EEPROM. Then at the end, I had to transmit a NAC. So after 10 bytes, you would set this bit to 1, and then at the end of that byte, it will generate a NAC for you. We have bits to transmit a stop condition and a start condition, and then here's that software reset bit that we need to set before we can modify these registers. Now, here's another difference between certain chips that you have to watch out for. The MSP430, when you set this bit here, the start bit, that will send the start condition and the address of the peripheral with the read or write bit set according to how UCTR is set. Not all chips do this for you. Some chips, when you set the bit to do the start address or the start condition, it expects you to send the address as if it were a piece of data. The MSP430 does it for you. Just make sure you know what your chip is doing so that you're not sending the address twice, for example, or not sending an address at all. If you're expecting the chip to do it for you and it's not, you're going to run into problems. Below that, we have, as you can see, our baud rate registers. We also have a status register, which not too much useful in there for us. All chips, you'll have these two buffers, a receive buffer and a transmit buffer. This is where we actually read and write data from. When you write a byte in here, it gets sent out on the I2C bus. When you're reading bytes from a peripheral, they're going to show up in that RX buff. And then we have settings for our own address if we're acting as a peripheral. We won't be using that at all. And then an address for the peripheral we're talking to, which can be up to 10 bits long. We're going to be using the 7-bit version. This is a chip, as I mentioned last week. Some chips will automatically shift the address for you and add the read-write bit. This is one of those chips. So we take the 7-bit address of whatever peripheral we're talking to, we put it into this register, and it takes care of everything else for us, which is really nice. Down here we've got interrupt enables, which we won't be using. But we also have interrupt flags, which we will be using. These flags get set whether or not we're using interrupts, and they're a good way to tell what's going on. These flags get set, for example, when start conditions are complete, when we're transmitting, when the transmit buffer is empty, when the receive buffer has received a complete character. These will tell us when certain events have happened so that we can act on them. So that's just a quick overview of the registers. As you can see, we can set these just by writing a hexadecimal number to them, or the MSP430, like many microcontrollers, will have an include header file, In the case of the MSP430, it's called MSP430.H. And these names here, UCA10, UCMM, UCMST, you could actually use those directly in your code, and it will know which bit you're talking about in these different registers, which is really handy. It makes the code a lot easier to read instead of just having a hexadecimal number, which then, you know, if you're a good programmer, you'd have to put a comment next to explaining what it does. This makes it a lot more evident what you're actually writing to the registers, and so it makes it easier for other people to read your code. Okay, so now we're back from looking at the PDF. Let's take a look at actually setting up those control registers. What options do we want? Well, we basically figured it out by looking at those registers. We need to set the two main control registers to the following values. First, we need to set that software reset bit. That's the most important part. If we don't do this, we're probably going to crash the processor or have unexpected results that may end up with corrupt data on the bus. Then we set the control 0, the 3 bits we're setting here. Remember how I said you can use that include file so that you can write the names of the bits? Well, this one, UCMST, that's setting us as the controller. UC mode 3, that's selecting I2C mode, and UC sync is also setting the synchronous mode bit. As I explained here, set the module as the controller, I2C mode, synchronous mode. Control 1, we're going to do UCS cell, that's actually 2 underscores, SM clock. That's saying we want to clock this peripheral from the SM clock. And then because we're writing to this peripheral, this register, we need to make sure that we keep that software reset bit set, so that's why it's added there as well. As I just said, we're going to be using SM clock. Then we're ready to set the baud rate divisor. We're going to be running at 6 megahertz. There's a typo there, it should say 60. So we're going to set baud rate 0 to 3C. Because our divisor is only 8 bits long, we can just set the top bit to 0. And actually, we don't even necessarily have to do that. It's just good practice. It will be 0 upon reset, but we should never assume that it's in reset state. Something else could have written to that in the meantime, so we always set it to 0. So the full 16-bit value is 003C, so it's going to divide by 60. Then we need to configure the I/O pins. Now, many microcontrollers allow peripherals to be connected to whatever pin. Some microcontrollers offer a lot of flexibility. The PIC microcontrollers will let you choose almost any pin on the chip, which is really nice. The MSP430, like many others, are hardwired. So we're using the Universal Serial Block B, because that's the only one that supports I2C, and we're using block 0. So it's going to be coming out on P3.0 and P3.1. This is SDA and SCL, as you can see there. Unlike other things, we're not allowed to remap it elsewhere. So we're going to have to remember to set these to the I2C peripheral. We need to tell the chip we want the I2C peripheral to have control of these pins. We don't want them to be just regular GPIO. So this is actually taken care of in the GPIO section of the datasheet. So on the MSP430, every port has a register called cell. In this case, it's port 3, so it's going to be P3 cell. If we set each bit in that register represents an actual physical pin. So we're going to have bits 0 and 1 because we want port 3.0 and 3.1 as peripheral functions. So we just need to set P3 cell to, we can either set it to a hexadecimal value, 0x03, or the header file includes names for us again, so we can use bit 1 and bit 2, and that'll do the same thing. That's a little bit more readable, so that's usually what I do. And then these pins are now selected to be data and clock for us. And that process is broadly similar. Some chips, when you enable the I2C module, it will automatically change the GPIO for you. On other chips it won't, so you just need to check and see what you need to do. At this point, we're essentially ready to enable the chip. We can bring the I2C module out of reset and start communicating. So if you know your C syntax, you can see we're unsetting that software reset bit. We're connected to the bus and we're ready to communicate. We need to set the peripheral address of whatever chip we want to talk to. We can do that now, or we can do it when we actually go to send bytes. Typically at this point when I'm writing my code, I would send a start followed by a stop, connect my oscilloscope or logic analyzer to the bus, make sure that we're actually seeing a start and a stop so that we're actually getting output on the pins. And that will also reset some chips, although you can't really rely on that working. If I'm having problems at this point, I will have the chip go into an infinite loop, sending either random values or the same value over and over while I debug. So I'll change different register values, reread the data sheet, make sure that I have everything set up correctly. So let's actually send some data. So those same registers, the control 0 and control 1, we're going to be using those, as well as I2C SA, which has the peripheral address, the transmit and receive buffers, and also those interrupt flags. Those are the registers that we'll be using to actually control communication. So at this point, we're going to take another quick look at the data sheet. So let's switch back to that quickly. Okay, so when we actually go to operate as a controller transmitter, of course, they're using problematic language here, but hopefully they'll update these data sheets at some point. So we initiate this mode by writing the desired address to the address register for the peripheral, setting the size with that 10-bit or 7-bit address, which we've already done, setting transmit for transmitter mode, and then generating a start condition. The module checks if the bus is available, generates the start condition, and transmits the address for us. The TX-IFG, which is that transmit flag, is set when the start condition is generated and the first data to be transmitted can be written into the transmit buffer. So as soon as we see that flag set, we can write our first byte. As soon as the peripheral acknowledges the address, the STT bit is cleared. So we can also watch that to see if the peripheral is acknowledging the address. The data written into the transmit buffer is transmitted if arbitration is not lost, which it won't happen because we're the only controller on the bus. The transmit flag is set again as soon as the data is transferred from the buffer into the shift register. So we can actually just keep writing bytes to that transmit buffer as soon as we see that flag set. If we happen to take too long and there's no data loaded before the acknowledge cycle, the bus is held. So it'll actually hold the clock line low and wait for you to send the next byte, which we want to avoid, obviously. Setting the stop bit generates a stop condition after the next acknowledge or not acknowledge. If it's set during the transmission of the address or while we're waiting for data to be written into the buffer, a stop condition is generated immediately. So this is sort of complex, but this is an important thing to point out on the MSP430. Even if we're only sending a single byte of data, we need to set the stop bit while the byte is being transmitted. Otherwise, it's going to try and immediately send another byte afterwards. Otherwise, only the address is transmitted. When the data is transferred from the buffer into the shift register, the flag is set, and then the stop bit may be set. So you'll see in our code we have to handle that as a special case. If we're only sending one byte, basically as soon as we load the data into the transmit buffer, we have to set the stop bit. If it does not acknowledge the transmitted data, then we get that NAC flag set. Then we have to either send with a stop or a repeated start. If we get a NAC and we've already written data into the transmit buffer, it's discarded. That's a good thing to know. If this data should be transmitted after a repeated start, it must be written into the buffer again. So this is basically just very simple how the flow goes. There's actually a flow chart here which can be handy to show you exactly what happens at each step, which I've had to refer to when writing this code. So that's just a quick overview of how it works on the MSP430. So, as we just saw, the process is going to be broadly similar on most microcontrollers. Ensure the peripheral address is loaded. There will be a register bit to send a start condition. As I said, some chips will also send the peripheral address at the same time as the start. Others might require you to send it separately. Then you load each byte of data to be sent into the transmit buffer. Between each of these steps, we check the flags. So We check to see, is it ready for the next byte? Was there a not acknowledge received? And then we take different actions depending on that. So if we actually go look at our basic code example, this is after everything's been set up. The first thing we do is we set the UCTR bit, so we're transmitting, and we send the start. So that's going to send a start condition followed by the peripheral address with the read-write bit set to write, which is a 0. Then we wait in this while loop until we can put the first byte of data into the transmit buffer. As soon as that flag is ready, it'll go on to the next line where we load the first byte in to the transmit buffer. The reason we're sending that first byte outside of the for loop below is because we have to send that first byte to be able to check if an address NAC happened. This is another quirk of the MSP430. So we start sending that first byte, then we check to see if the start condition completed. If the start condition completed and we have a NAC flag set, that means that the peripheral did not acknowledge the address we sent. We must immediately send a stop, which we do, and then we wait for the stop to complete, and then we return from this function with an error code. However, if it does acknowledge the address, then we go down to the next while loop here. We wait for the buffer to be clear. Then from byte number 1, remember the first byte we sent was byte 0. From byte 1 until however many bytes we're sending, we loop through this little for loop. We load the data into the buffer. We wait for the buffer to be clear. We check to see if we got a not acknowledge from the data we sent. If we got a not acknowledge, we send the stop bit and then we return from the function. Otherwise, we just send all our data, and then at the bottom, we send the stop bit. So pretty simple. If you look at how many lines of code this is actively sending I2C data using the hardware peripheral. Much smaller code than would be required to bit bang it or do it via GPIO. If we want to read some data, it typically looks similar to writing data. We just read from the receiving buffer instead of writing to the transmit buffer. That's a typo there. It should say TX buff. The MSP430 has a few quirks compared to other microcontrollers. Unlike most other microcontrollers, like we just saw in the data sheet, we must initiate sending the stop bit before reading the final byte. If we wait until after that, it's going to read another byte, which we may or may not want. So there's another bug I'm trying to fix where for some reason we're missing a byte of data. I fixed this by reading another byte of data past what we should need to read. You'll see this in the code. I'm still not sure what's causing this. Hopefully it's not a hardware issue, but at least the code does work, which is good. So the same process as before, send a start condition, but this time the transmitter bit is off because we want to read from the device. We start reading bytes from RxBuff, checking the byte received flag in between each byte. When we've read the required number of bytes, send a stop condition. It's going to handle everything else for us. It's going to handle sending the address to the peripheral. It's going to handle generating the clock cycles and the acknowledge. So let's look at the code example for this. Same thing, essentially. We clear the transmit bit, UCTR. Then we send a start. So this will send the address with the read bit set. So it's the address for reading data. We wait for the start condition to be completed, and then we check to see if we got an acknowledge. If we didn't get an acknowledge, just like before, we send a stop, and then we return from the function with an error code, NAC address. If it did acknowledge, we wait until we're told we can read the first byte, which is what that RxIFG flag does. If we're only reading one byte, remember this weird quirk, we have to immediately set the stop bit, while the first byte is being read, if it's single byte only read. We set the stop bit, we clear that flag, the transmit flag, and then we read the data out of the buffer. Then we wait until the stop is completed and we return success. So if we're just reading one byte, it's that simple. Otherwise, we go into a for loop doing the same thing. If there's a special case here, if we're on the last byte, remember we have to set the stop bit before we read the byte from the receive buffer. So If we're at the last byte, then we need to set the stop bit, read the byte of data, and then wait for the stop bit to complete, break out of the loop. Otherwise, if it's not the last byte, we just wait for the next byte to come, read the byte, and then go back through the for loop. At the end there, you can see dummy byte. So if I remove that line of code, we end up getting cut off and we don't read the final byte. I don't know why this happens. This actually does cause another byte to be read from the chip, which is just garbage that we throw away. But if we don't do this for some reason, it won't give us that last byte. So it's just an unusual quirk. I'm not sure why, but it does work. So let's actually go look at Code Composer Studio, and we'll take a sort of quick tour of the full I2C library that I've written. Okay, so let's take a close look at the library I've written. This is an example code that you can download and play with if you want. So I've implemented I2C as a class in C++. So this first function here is the constructor function. This is called when the user wants to start communication with an I2C peripheral. It gets passed in the speed that we want it to run at, and it also gets sent the address of the peripheral. I actually wrote a little bit of math here that will calculate the baud rate for us. So we can pass in 100 kilohertz, 400 kilohertz, whatever. It'll take care of calculating those baud rate registers for us. Then, as you can see, we make sure that the... I'm not actually sure why I have this line in here, but we set the direction to be inputs for some reason. Then we set those two bits, bit 0 and bit 1, to be SDA and SCL like we saw earlier. We set the device into reset, the I2C peripheral. Remember, this is that really important step. Before we can change any of these registers, it needs to be in reset. Just like the example code I showed on the slide, we set the UCMST bit, UC mode 3, which is I2C, UC sync. In the control 1 register, we select SM clock, and we make sure that the software reset is still set. Then we write in the calculated baud rate, which we calculated up here. If we were given a peripheral address, we load that now. If we weren't given a peripheral address, then we just ignore it for now. Then we bring it out of reset and we're ready to go. Now, I've taken all the I2C transactions that you can do and put them into a big function called transact. You pass it the data, how long the data is, and then what type of transaction you're doing. So if we are writing, then it's just the code we saw earlier. We set the transmit mode bit as well as the start bit. It sends the address and the start condition. We send the data that we're writing. We check the flags for not acknowledge. If we get a not acknowledge, we send the stop. We already saw and went through all this. Same for the read. This is the code we just looked at. We make sure transmitter mode is clear. We send a start condition. We wait for the start condition to be complete. And then we read that dummy byte at the end. I also have a combination one where this is often what happens when you're communicating with a peripheral. You need to write a single byte and then read many bytes. So I've combined that into one function, which is nice. Actually, it could be more than one. So we might write a few bytes and then read a few bytes back, which makes it handy. And then I also have a test mode. This is just a little function I wrote. It's actually a linear feedback shift register, which essentially just generates all the values between 0 and 255 in a random order and sends them over and over and over again. This is what I use if I'm debugging. If something's going wrong, I can enter test mode and then take a look at the actual SDA and SCL lines. And then I have another function down here, change address. We pass it the address we want, and it will just write that into that register for us. So pretty simple, right? Now, if we want to actually use this to communicate with something like an SHT21, then we write another class in C++. At least this is how I implemented it. So the SHT21 can get temperature or humidity. I'm not going to go into all the details of how this chip works, but this is how we use this library that I've written. So we store, well, if we actually look at the main, we create an I2C bus using that constructor function running at 400 kilohertz. Then we actually have an SHT21, and then we also have a BMP180. Both of these get passed a reference to that I2C bus so that they can both use the same bus. So if we actually look at these, that bus that it gets passed gets stored into a variable called bus access. This is just a way for this class to access that I2C bus. Don't worry about these details if you've never used C++ before. What's important here is if we look at the actual getTemp function, we allocate a buffer of 10 bytes, which is probably more than we need. Then we call that change address function to set it to the SHT21 address, which is actually defined in the header file right here. SHT21 address is 0x40. After that, we send the trigger temp command, which is F3. That triggers a temperature measurement. We call that transact function with the buffer as the argument. We want to write 1 byte. So it writes that 1 byte out. Then there's a unique feature of the SHT21. As it's converting the temperature, if you try and read from it, it will just send you not acknowledges to the address. So what we do is we try and read the 3 bytes from it. If it doesn't work, for example, it returns NAC address. We wait 15,000 cycles, then we try again. We just keep doing this until we get those 3 bytes. Once we have those 3 bytes, that's the raw temperature data, as well as a checksum, which we're not going to use. We use the formula from the SHT datasheet to calculate the temperature, and then we return the temperature. So actually using our I2C library in a function is quite simple. We just call change address to set the address we want, and then we use the transact function to write or to read data. It's pretty simple. It's the exact same thing for humidity. The only difference is we're sending the trigger humidity measurement byte. We do the same thing. We read 3 bytes from it, and then we calculate the humidity. There's also functions here to turn the heater on and off, which aren't actually used in this example code. But I've done all this as C++ because it makes it really easy to break all these things into pieces, where we can have the I2C library, and then that library can be shared by different chips that are on the bus. It just makes it a lot easier. So that's just a quick overview. All this code will be posted. When we do the question and answer session, I expect there's going to be a lot of questions about things. If you have questions about C++ syntax or C syntax, you can send those to me personally through Twitter or by emailing me, and I'll be happy to explain things to you. But if you have questions specifically about I2C and about implementing it, then ask those in the question and answer session. So, putting it to work, we want to actually communicate with something. This is that SHT21 example I looked at. So, whenever you're working with a new sensor, the most important thing to do is to study the important parts of a datasheet carefully. We want to know specifically the things we're looking for in the datasheet for a part we're working with. We want to know what the address of that peripheral is, what its register map is, so what internal registers it has, and what bits get read and written to them. And this is a skill you'll develop over time. You'll start to learn what the essential pieces of data you need are. Because often you can ignore big chunks of a datasheet if you know what you're looking for. So let's take a look at the SHT21 datasheet, and we'll note down important parts. So let's go dive into it. Okay, so we're just going to take a quick look at the SHT21 datasheet. We're not going to go into the detail of how this particular chip works. we're just going to show what it is you need to look for when you're working with an I2C device. So it's going to give you an explanation of the chip. It's going to show you the dimensions of the chip and how it works. What we're interested in, it's going to show you all the performance of the sensor and operating range and all the different temperatures and how it affects its accuracy. What we're interested in is the I2C bus. So, it looks like we're getting close. Communication with the sensor, explaining how I2C works. Aha, here is a table of all the commands. So, we can trigger the temperature measurement, trigger the relative humidity measurement. These different hold and no hold, these will either hold the bus low, making us wait for it to finish, or the no hold version is what we use, where we let it do its measurement and we just occasionally check to see if it's finished by checking to see whether it acknowledges its address. It's interesting that it doesn't actually give you the address anywhere. Often data sheets do this, it's really odd. But in these examples, you can see it shows you, let me zoom in on this, the I2C address plus right, so which is 1000000, which is 80. And then here's the address plus read, 8, and then a 1. So we can figure out from that that the 7-bit address is 0 by 40. It's interesting that it doesn't just say that somewhere. I found that a lot of I2C chips are like this. They just won't give you the address straight out anywhere. It'll be in the examples. Sometimes it'll give it to you, but often not. And then here are the formulas that I use to actually convert those raw data from the registers into the relative humidity and into temperature. So this is a pretty simple chip. All we have to do is send one of these measurement codes. So we write these bytes on the I2C bus, and then we read 3 bytes back. So you can see here, this is this chart over on the right. This is how I implemented it. Oh, I'm so used to shift scroll moving to the left and right. So we send the address and the write, we send the command, we wait 20 microseconds, we send stop. That's how I've implemented it. It starts measuring. Then a little while later, we try and send the I2C address plus the read bit. It responds with a not acknowledge. This means that it's not finished measuring yet. We wait another little while, we try again. This time we get an acknowledge. Okay, good. We can read the data. You can see it reads the 2 data bytes out and as well as the checksum. This is how I've chosen to implement it. The other way to implement it with this particular channel is it actually will hold the bus low during the measurement and then it'll send you the 3 data bytes once it's finished measuring. That ties up the bus. There's reasons why you might want to do it that way to get the result as soon as possible, but it doesn't really matter too much. The important things I want you to note from this data sheet is that you need to find these important things. You need to find, if it takes commands, you need to find a list of the commands. If it has registers, like this also does, down here it explains what the user register actually does. You can change the resolution of the measurements. It'll tell you if it's running off of battery life, if the battery's getting low. You can enable the on-chip heater. There's other things. So these are the important things you're looking for. As you can see, it also has a soft reset command. We could actually send that after initializing the chip in the constructor function for the SHT21. I think I may actually do that in my code. And then it shows here examples of how to actually read and write to the user register. It also shows how to use the CRC checksum. If you're using some sort of application where it's high reliability and it needs to be sure the data is correct, then you would implement the CRC checksum. If you're just doing something simple like we're doing, you can just ignore the checksum and just assume that the data is correct because it's unlikely to be corrupted on a bus as small as what we're doing. And this is all you need to know. Most data sheets for I2C devices will actually have a whole section explaining how I2C works. It'll show you, what all the timings are, how start and stop sequences work. So if you forget anything, it's kind of nice they have a reminder in here of how the basics work. It shows you the different speeds it can support. So you can support up to 400 kilohertz. It gives you all the different times for how long you have to hold each thing high or low. This would be useful if you're writing a bit bang version and you need to know the exact timings. So basically, you just need to find the important data in the data sheet, and you can essentially ignore the rest if you're just implementing something simple like we are. So let's go back to the slides and finish up. So notes on the SHT21. The most important pieces of information, just like when you're working with any chip: address is 0x40. 5 commands we might want to use: trigger temp, trigger human, write and read the register, soft reset. After sending a trigger command, we simply keep issuing reads. As we saw, it'll knack the address if it's not ready. Note the formulas that we use to convert the raw values into actual temperature and humidity values. And then this is a summary of the code that we just looked at not that long ago. We create a buffer for the values. We send the humidity trigger command. We then try and read from the chip. It's going to send not acknowledges. We repeat this until we get an acknowledge. Read the 3 bytes. We put those first 2 bytes, which are the important ones, into a 16-bit integer. Then we calculate the humidity. And then we can do whatever we want with that. We could print it out to the user. We could send it to the cloud. The code example, this is what we looked at before. We create a buffer. We set the address to the SHT21 address, trigger humidity. We already went over this. When we're at the end there, you can see it returns the humidity as a double. So once that's returned, reading temperature, the only difference is the actual command code. We already sort of went over this. The code example for getting the temperature is the same. The only difference is the formula for calculating the temperature. We already sort of looked at the full SHT21 library, so we can skip over that. Now let's actually do something with the data. So the simplest thing we can do is just display them to the end user over a serial link. We won't be getting into how to actually set up the serial link, but we will be using a timer interrupt to put the processor to sleep. When it wakes up, it'll sample the humidity and temperature, send it to the end user. So let's go take a look at that main function again. All right, and then to finish off, we're just going to actually do something with this data. So we'll take a quick look at this function I wrote. Up here is all the stuff setting up the clock and whatnot. This is all specific to the MSP430, and so it's not really relevant to this lesson. We create the I2C bus, and we pass it into the SHT library I wrote. We also create a UART at 115.200. And then a timer that will actually trigger every now and then. Eventually we get down into this while loop where it gets the humidity and it gets the temperature, and then it prints them, it formats them into this string buffer, and then it prints it to the screen. We start the timer, we go to sleep, it waits until the timer triggers, and then it does it again. It works out to every few seconds. So make sure we're actually recording this. Yep, all right. Let's actually run this chip. So we'll go into debug mode. So I've actually got the board here set up with the Sensor Hub booster pack. Okay, so we're actually going to start the debug here of this example that I wrote. We've got a terminal here open to the serial port of the chip, and so when I hit start, you can see it's measuring the humidity. It's a sweltering 67% right now. The temperature is about 25 degrees. That's why you can see a bit of a sheen on my forehead. And it's going to update this, as you can see, every 5 or 6 seconds. And that's pretty simple. I mean, we're reading and writing from an I2C chip with not that many lines of code. We can go back, if we actually pause, we can actually have it break when we go to get the humidity. Now we can go through this if we want. See it go through. Oh yeah, step out of that. What we want to see is this. So of course it changes the address, so it calls that function down here to change the address. It sets that register to the correct address. We go back. It loads the buffer with that humidity trigger, and then we'll just skip ahead. You can see how fast that actually happens. So now that raw data that comes from the chip looks like that. 38376 doesn't really mean a lot, so it has to go through this function. If we skip ahead, actually we have to jump out of that. We'll see the humidity has now been calculated to 67.8%. That's actually showing exponent plus 1 for some reason, but free buffer. I mean, it's pretty simple. I've only got a few minutes left of my laptop battery here, so let's get back to the slides and finish this off. So, summary. This is what I wanted to get across. When you're working with I2C, the most important skill is reading data sheets, getting the essential information. Both the data sheet for the microcontroller that you're going to be using and the data sheet for the peripheral you're going to be communicating with. This is an important skill that will develop with use. If you have questions about this, please bring them up during the Q&A session tomorrow night. Most microcontrollers that have I2C hardware support work in generally the same fashion as I showed today. Another important skill is being able to identify the quirks of the particular I2C peripheral and what strengths and weaknesses it has versus other microcontrollers. This is again something that comes with experience. Once you've worked with microcontrollers for a while, you start to learn which ones have easy to use peripherals. So the key data points: setting the microcontroller baud rate, enable the I2C module, sending the peripheral address, generating start and stop conditions, acknowledge and not acknowledge while reading. What are the addresses of the peripherals you're working with? Does the chip automatically convert the 7-bit form to the 8-bit form, or does it expect you to do this? What registers does the I2C peripheral have? Does it require you to write a register address before reading, or does it simply respond to commands with data? Make sure you're able to detect not acknowledges from the peripherals and handle these in software. So, I know this was a little bit rushed. I was trying to squeeze this all into an hour. So further reading, if you want to get even more in-depth look at I2C, I highly recommend the book Mastering the I2C Bus by the legendary engineer Vincent Himpy. He's been featured on a bunch of different podcasts. He's a really, really cool guy. There's the ISBN. It's available from Elector as an ebook for 24 euros. Print copies are basically impossible to get. I'm lucky enough to have a paper copy sent to me by him, signed by him, which is really cool. The full I2C standard is available for free download from NXP. There's the link to it. It's kind of hard to see, but if you download these slides, you can click on that link. Next week, we're going to be starting with OneWire, which has many similarities to I2C, but it does not have a clock line. So make sure that you're signed up for that class and tune in. We're going to be bringing everything we've learned together in week 4, where we combine everything together, OneWire and I2C, and we do something with it. So thank you so much for watching, and hopefully you learned something, and hopefully we will see you next week, and also tomorrow night at the question and answer session.